Welcome to the topic of function integrability. Let's delve into the world of mathematics and explore the intriguing concept of integrability. A function is said to be integrable when we can determine its integral within defined boundaries, revealing to us the signed area residing beneath its curve. This integral area holds significant meaning in mathematical analysis. To further grasp the notion of integrability, let's journey into the realm of Riemann sums. Using this method, we break down the area into smaller, manageable rectangles, summing their individual areas to approximate the total area under consideration. Moving ahead, we encounter the vital prerequisites for integrability: a function's bounded nature and the convergence of the sum of rectangle areas. The continuity of the function over the given interval serves as a foundational pillar for achieving integrability. Now, transitioning to the criteria that define integrability, we explore how a function must maintain continuity across a closed interval a(b) to be classified as integrable, even allowing for a finite number of discontinuities. Let's bring theory into practice with a real-world example, calculating the area beneath a velocity-time graph to unveil the distance covered by an object, illustrating the practical applications of integrable functions. Integrable functions find extensive utility in various fields. They are indispensable in physics for analyzing motion, in economics for modeling cost and revenue functions, and in engineering for system analysis. In summary, the key to determining integrability lies in understanding concepts like continuity, Riemann sums, and the convergence of limits. These elements collectively play a pivotal role in identifying integrable functions. As we approach the culmination of our exploration, we invite you to engage in an interactive quiz to reinforce your understanding of function integrability. Thank you for accompanying us on this enlightening journey. Keep exploring, keep learning.